Welcome back everyone. So in today's video we're going to solve two AITS problems from circuits. So this is the first problem. So in this question we have a switch in position A for a long time. So this is the active circuit, and then it's given that it suddenly switched to side B. So we have to find the maximum speed of the rod. Okay, so initially it's simply an LR circuit, and now as the switch is in position A for a very long time, we can treat the inductor like a short circuit because the current would have reached its stable value, right? So the current in this circuit is simply E divided by R, and it is flowing in the clockwise sense, right? Okay, so now we switch it to side B, so this circuit is inactive now. So now we have an inductor connected across a conducting rod. So now we are going to use the fact that the current in the inductor branch does not change instantaneously, which basically means that let's say we turn the switch from A to B at time t equal to 0. So at time t, which is 0 plus, which is a very short time after time t equal to 0, the current in the inductor will still be the same as it was before t equal to 0. So before switching, the current in the branch was E by R in the downward direction. So just after switching also, it will be E by R in the downward direction. There is one particular case in which this does not hold, and that we'll see in the next question. So in the inductor branch, there is a current of E by R. So this is the situation after t equal to 0 when the switch is turned. Okay, so now guys, we have an inductive circuit. So there is no resistance present here. So the energy is going to oscillate between the energy stored in the inductor and the kinetic energy of the rod, and it's not going to dissipate as heat because there is no resistor present in the circuit, right? Okay, so now in the the current in the rod is flowing in the upward direction, and the magnetic field is given to be out of the plane in this question. So if you do I cross B, the force comes out to be towards the right. So the ILB force on the rod will be towards the right. Okay, so let's say so at time t equal to 0 plus, the current in the circuit is E by R. Let's say at any general time t, the current in the circuit is I. Now guys, so our problem is to find out the max speed of the rod. Okay, let's write the dynamics equation for the rod. So the only force acting on the rod is ILB. So, and this will be equal to the mass times its acceleration, dV by dt. So if you observe something, the acceleration is positive as long as the current is flowing. Okay guys, so now as I said earlier, the energy is going to oscillate between the inductor's stored energy and the kinetic energy of the rod. So the energy at any general time t is half Li squared, which is the energy stored in the inductor, plus half mv squared, which is the kinetic energy of our rod. And this energy is obviously conserved, right? Because there is no resistor in picture. So what that means is the kinetic energy will be maximum and the current is minimum. So which basically means as the velocity of the rod is increasing, the current in the circuit will decrease. Okay, so basically the kinetic energy is max when current I is 0. So the motion of the rod looks something like this. So initially the rod has 0 velocity and the current in the circuit is maximum. Then at the instant when the current is 0, the rod achieves its maximum velocity. Now you can consider the induced EMF VBL. Because of this, there will be a clockwise current will start running, and now the rod is going to decelerate. And in the extreme position, again its velocity will be 0 and the current in the circuit will be I max, and this will keep on performing this oscillatory motion. So the rod will perform an SHM, and you can also find out the equation of motion by solving the KVL equation and solving the dynamics equation together. But again, in this question we only have to find the maximum velocity. So let's say it is half m V max squared. So this will be equal to the initial energy stored in the inductor, so which is half L times the initial current. Initial current is E by R, so this will be E by R squared. So from here the maximum velocity comes out to be E by R square root of L by M, and that corresponds to option A. Okay, so now let's move on to the next question. Okay guys, so in this question we have a linear electrical circuit, and they've said we perform two particular operations. So operation 1 is that S1 is closed at time t equal to 0, and S1 is this particular loop. Okay, so this is the active circuit, and after a time of 2 seconds has passed since operation 1, S2 is now toggled. So it's switched from this particular location into this particular location. So then we have to figure out the value of the current passing through the resistor immediately after the operation 2 has been performed. So again, similar to previous problem, the initial active circuit is a simple LR circuit with growing current, and the current growth in the circuit I is I naught 1 minus e to the power minus t by tau. After a very long time, again you can treat the inductor like a short circuit, and the current in the loop I naught is going to be E divided by R, which is 7.5 amperes. Okay. So now the time constant of the circuit is again L by R, which is 2 seconds. So now let's figure out the current after 2 seconds. So this comes out to be 7.5 times 1 minus e to the power minus 1, and e to the power minus 1 is 0.37. So this comes out to be 4.725 amperes. So after 2 seconds, a clockwise current of 4.725 amperes is circulating in the circuit. So now the thing is, we toggle switch S2 to the other location. So let's draw a new diagram. Again, discussing the initial condition at t equal to 2 seconds, current of 4.725 amperes was circulating in the clockwise sense. Okay. So now what happened? So this is the situation at time t equal to 2 seconds. So now what we did is we changed the position of the switch and we connected the other circuit, and we connected both the inductors together. So now this is the active circuit. Okay. So again, staying with our principles, we know that the primary role of the inductor is to delay the change in current. So the moment we change the switch, current in the inductor branch should remain the same. It cannot be changed instantaneously. But in this question, if you observe, there are two inductors in picture. So just before closing, this guy had zero current passing through it, and this inductor had a current of I passing through it. Now the thing is, we have two inductors fighting with each other. So now we have two competing inductors in this circuit, right? So something needs to happen. So definitely there needs to be a change in current, right? Because this inductor number 1 wants the current to be I, and inductor number 2 wants the current to be 0. So actually what will happen is the current will change instantaneously in this particular case. And let's try to understand why that is. And again guys, we are talking about the time just after the switch is closed. So at time t equal to 2 seconds and 2 plus. Okay, 2 plus is just after the switch is closed, and let's say the current flowing in the circuit at t equal to 2 plus is going to be I. So let's name this current as I star for now. I star is the initial current in the L1 inductor. So now obviously, as they are in series, the same current must flow everywhere. As you guys can see, the current actually changed from I star to I. And this happened within a very short duration. So the difference between 2 seconds and 2 plus, so plus, by 2 plus I mean 2.000, like imagine infinitely many zeros and a 1. So this is what I mean by 2 plus. So within a time difference of 2 seconds and 2.00 and so on, a finite change in current actually happened. Which means if you observe, like calculate delta I by delta t, this actually tends to infinity, right? Because a finite change in current in an infinitesimally small time frame actually happened, which means di by dt, which means that rate of change of current in the circuit at this moment of t equal to 2 seconds is very high. So what that means is, now if di by dt tends to infinity, then what that means is the potential drop across the inductors is also very high, right? It will tend to infinity, because what is the potential drop across an inductor? It is L times di by dt, right? Let's try to write down the KVL equation for this loop. So we can say E minus IR, and across the inductor L1, it is going to be minus L1 di1 by dt. So the rate of change of current across inductor L1, and across inductor L2, it is going to be L2 di2 by dt, and they should all add up to 0. Now guys, as we discussed, the rate of change of current in this circuit is extremely high, right? And so the thing is, these two terms are orders of magnitude larger than E and IR. So it's like comparing like 2 volts with 2 billion volts. So we can actually neglect that E and IR from this equation. And finally, our equation is just L1 di1 plus L2 di2 equals 0. Okay, so now let's integrate this expression. So what we end up with is L1 delta I1 plus L2 delta I2 equals 0. So delta I1 is basically the change in current in inductor L1. Initially it was I star, and right after switching it became I. So this is going to be I minus I star. And for the inductor 2, the change in current, initially it was 0 and finally it is I. So this is simply going to be I. And this should add up to 0. And once you solve this equation, you'll get the answer as 1.89 amperes. So yeah, that was this question. So if you observe this thing, this quantity over here. Now guys, the quantity Li is basically the flux, the total flux of the magnetic field passing through the inductor, right? L1 delta I1 is just the change in flux in inductor number 1, and L2 delta I2 is like the change in flux through inductor 2. So this is kind of like saying that the total flux across inductor L1 and L2 is constant or it is conserved, Okay, so this equation is the flux conservation argument basically. So yeah, so that was it for this question, guys. So now in the question they asked us the value in milliamperes, so this will be 1890 milliamperes. So that was it for this video, guys. I'll be bringing more videos in the future. So if you enjoyed the video, please do like, share and subscribe, and that's it. Thanks for watching.